Hey guys, Active Learning here. Welcome back to another video. In today's video, we'll be discussing transfer learning approaches, and this is part 2 of our transfer learning series. The first video was 3 weeks ago. Sorry for my terrible upload schedule. I've been pretty busy over the past weeks, so I haven't been able to upload as much. But hopefully in this week, I'll be uploading more frequently so you guys get more content, alright? So let's jump straight into our video. So today we're going to talk about the approaches we can take in transfer learning. In our last video, we kind of discussed the basics of transfer learning and what transfer learning is. But today we're going more in depth, okay? So these are the 3 approaches that you can take, and today we'll be discussing each of them in depth. Alright, so let's get started. So the first one is called pre-trained network as a classifier. So what this means is that we're basically taking an already trained model. It has to be trained on a similar data set, okay? And then we apply it directly to our tasks. This means that we're using the model without making any changes, no extra training, no tuning, nothing. We just apply it directly to our new data set, right? And this is why it has to be a similar data set. The pre-trained model has to be on similar data set, or else it won't really work, right? For example, if our pre-trained data set is on cats and dogs, and then we suddenly apply this to cancer disease, the classification, that won't really make sense, right? So we need to have a similar data set to be trained on. And all we have to do actually is to download the network architecture from online, and then we predict it directly to our new data set. And in the next video, I will actually show you how it's done. It's actually really simple nowadays. With TensorFlow, you can just use TensorHub, and then you can just download the model within a URL. It's really simple. So yeah, that's what pre-trained network as a classifier is. Now let's talk about using pre-trained network as a feature extractor. If you guys watch my convolutional neural network video, you know what features are. So basically, using pre-trained network as a feature extractor, we're using the feature extraction part of the pre-trained model, and then we might change the classifier or output layer and the input layer, and then we freeze the weights, which means the learned features, and then replace the output, right? This will save a lot of time because we're using the saved features, okay? And typically we do this by using pre-trained model on a larger data set, right? So here's a good image that I think it's helpful to visualize. I got this from Daniel Burke, his YouTube channel. Okay, so this is our pre-trained model, right? It's trained on a large data set, for example, ImageNet, a very popular data set, by the way. And then here we are using EfficientNet, which is one of the most popular architectures out there. And then we're simply we're still using the feature extractor part, but we're changing the output layer, right? Instead of predicting 1,000 classes, we're only predicting 10. So our model actually trains better, right? Because in this feature extractor part, we might be trying to classify like 1,000 different classes, but those might overlap with our 10. So we're better off and to predict 10 here. So yeah, and you know, we have to use a smaller data set here. That makes more sense, right? Okay, and this is also another image that I found to be really helpful. This is the VGG16 network, and in here we're simply removing the classifier to add our own classifier, right? Instead of predicting 1,000 classes, we might only have to predict 2, and in this case, it might be cats and dogs or something like that, right? And instead of 1,000, 2 is sufficient. So it's a lot more efficient to only train 2, right? This is why we might prefer using a pre-trained network as a feature extractor instead of using a pre-trained network as a classifier, right? This will be more efficient. Okay, now we understand what pre-trained network as a feature extractor is. Now, finally, let's talk about fine-tuning. So far, the network architectures we used are based on based on models that are similar to our problem. What if our problem is completely different? Well, we can actually still apply transfer learning. So transfer learning works well on different problem areas as well. We just need to extract the useful features from the network architecture and fine-tune them to our own problem, right? So the formal definition of fine-tuning is jointly training the pre-trained models, non-frozen layers, and newly added classifier layers while freezing a few of the network layers used for feature extraction. And since we retrain the feature extractor layers, we make them more relevant to our problem. So this is essentially fine-tuning, right? Let's visualize, because visualization always helps. So in fine-tuning, we make a decision to freeze a specific layer of a pre-trained network, right? So we could freeze up to here. We can ignore these and freeze up to here, and ignore these or freeze up to here, right? So you have to remember that the deeper the layer, the more advanced the features will be, right? For example, in feature map 1, we might only be detecting edges and stuff, right? But in feature map 4, we could have like a whole human face or eyes and stuff like that, right? So the deeper it is, the more fit it is to the data set of our pre-trained network, right? So that's why we might actually want to freeze our model up here so we can ignore later on, right? The edges are really general, so we can actually apply the edge detection to a lot of different problems, right? So a lot of different problems in different domains, we can still apply transfer learning, right? So if we want to freeze our network up to 3, for example, we want to freeze it before this. This means that we're using feature map 1, feature map 2, feature map 3, and we're excluding feature map 4, okay? So yeah, this is how it works. And if you're wondering why we flatten it, for our fully connected layers, we have to flatten our two-dimensional images, right? Okay, let's move on. So then the question becomes, what's a good number of layers that we should freeze, right? Yeah, remember that feature maps get more and more specific the deeper the network, deeper in the network, right? So this means that the first few feature maps are very generic, so we can apply them to almost any different domain, right? If the domains are similar, we can even freeze up to the last feature map, right? And if the domains are very different, we might just freeze up to feature map 1 and then retrain all the rest of the feature maps, right? So that's what fine-tuning allows us to do. Now, so fine-tuning is actually still better than training from scratch, right? Even if the domains the models are trained on are completely different, fine-tuning is still better for our case if we're trying to train from scratch, right? So since we're randomizing our weights when we start a model from scratch, it will be very slow to find the optimal weights, right? Thereby converge slower. However, if we have fine-tuning, it allows us to use the model's weights that it ended with, right, for our previous data set, right? So thereby, we don't have to randomly assign weights. We can just use the weights that are pretty close, right? Pretty close, and then which allows us to optimize our model faster and converge faster. So fine-tuning is still very overpowered. Alright, okay. Now, when do we use each approach, right? There's a lot of stuff, right? So In the first scenario, if it is really similar to our data set, we can expect the more specific feature maps deeper in the pre-trained network to be relevant to our data set as well. So it might be best to freeze the feature extraction part of the network and only retrain the classifier. And in this case, it is not a good idea to fine-tune the network if our new data set is small. This is because a small data set doesn't have enough information to cover all possible features of its object, which makes it fail to generalize to previously unseen data, right? So in this case, the more fine-tuning we do, the more prone the network is to overfit the new data. So that's not good. And in the second scenario, since both domains are similar, we can freeze the feature extraction part and retrain the classifier, similar to scenario 1, right? But since we have more data, we can get a performance boost from fine-tuning through all or part of the pre-trained network with more confidence that we won't overfit, right? Fine-tuning through the entire network is not needed since the higher level features are related as the data sets are similar, right? So a good start is to freeze approximately like 60 to 80% of the pre-trained network and then retrain the rest of the new data, right? Now, for scenario 3, if the target data set is small and very different, then we might expect something else, right? Since the domains are different, we don't want to freeze up to the deeper end of the network feature maps, right? Remember that the deeper it is, the more specific and advanced the feature maps will be. And since they're different, that's not necessarily helpful. So it would be better to retrain the model from earlier in the network or not freeze any layers at all, right? We might want to retrain. And since our data set is small, right, we can just freeze the first third or half of the pre-trained network since the early layers contain generic feature maps like lines and edges. And those are very useful even if our data set is very different, right? And line sight and edge detection are based on weights as well, right? Those are basically weights. So we don't have to start from scratch. And this boosts our training efficiency by a whole lot, right? All right. And if our target data set is large and very different, then we might want to fine tune through the whole network, right? So, yeah, since the data set is large, we might want to retrain the entire network from scratch, right? However, remember that it is still very helpful to initialize weights from a pre-trained model so we don't have to randomize the weights, right? And this will make our model converge faster, remember? So here, since we have a larger data set, we can confidently fine-tune through the entire network, which means initialize our network using pre-trained weights. And that's different from here where the data set is small, so we can't actually apply fine-tuning through the entire network, right? And yeah, that's it for this video. I'll be uploading more frequently and I'll be doing some coding as well, so it actually helps to explain what I'm talking about here, because sometimes coding helps you understand stuff better. And I kind of realized that today's video is filled with text, and that's probably not a very good idea. So in the future videos, I will try to use more images to illustrate what I'm talking about, so it's easier for you guys to understand. And yeah, if you guys found this video helpful, please leave a like and subscribe. And yeah, sorry guys about my terrible upload schedule. I've been pretty busy over the past few weeks, but I will definitely be uploading more frequently. And if you guys have content suggestions, please feel free to leave them down in the comments below as well. And if you have any questions, you can leave them down in the comments below. So please ask any questions you have. So yeah, thank you guys for watching today's video and see you guys next time. Bye.